Okay, we're going to talk about friction now. So here we go. Here's a whiteboard eraser. So if I press hard on that whiteboard eraser, the friction is large enough the whiteboard eraser doesn't fall. But let's say I use my pinky, and let's say I don't press hard. The friction decreases, and the whiteboard eraser falls. So here, there's a large normal force, right? But if I don't press very hard, the normal force is pretty small. So what did we just figure out? What we just saw is that the frictional force is proportional to the normal force. If you increase the normal force, the frictional force increases. If you decrease the normal force, the frictional force decreases. They're proportional. All right, wonderful. Let's draw the force diagram. All right. Okay, so here's the eraser. The force is acting on it. Weight, right? And here, this is friction, right? Weight is this way, so friction has to be that way, because if no friction, it would fall this way. Now, let's say that this is the push. So we're kind of looking at it like, sort of like that, right? All right, so this is me pushing it, and then this is obviously the normal force, right? So I push it this way, the normal force is this way. So we're saying that this is in and this is out. Okay? All right. Now, so like I said, the frictional force is proportional to the normal force. Okay. Now, we don't really like proportional relationships in physics. We want like an equal sign, right? An equal sign. So do you think the frictional force is going to depend on this surface as well as this surface? Well, yeah. I mean, if this were ice and this were ice, that would be different than if this were sandpaper and this were sandpaper, right? So if you include the properties of the surfaces, then this proportion relationship becomes an equation. So now it says that the frictional force equals the normal force multiplied by this constant. This is a mu, Greek letter mu. And it's a constant, and it depends on the surfaces. The whiteboard surface and this surface. Okay? Now, actually, this is the truth. This is correct. So we put a little s here because this is static friction, right? So this is static friction because it's not moving. Later on, we'll talk about kinetic friction when something is moving along a surface. So the static frictional force is actually less than or equal to this coefficient, which has to do with the surfaces times the normal force. Now, why is there a less than or equal sign? So I want to explain that now. Okay. So pay attention to this, please. Okay, again, so the static frictional force is less than or equal to mu n. All right. So here's a table. And these numbers I just made up, but you'll understand. So I'm going to exert a force. I'm going to exert different forces on this box. So this is the force that I'm exerting on the box. So the force of me. And this is the force of static friction between, the tabletop and the bottom of the box. Okay? All right. So first of all, I'm going to exert a force of 0.01 newtons. Well, that's pretty small, right? So here we go. All right? So I blew on it, and I'm just guessing that the force is 0.01 newtons. Well, did it accelerate? No. So my force was, this way, but it didn't accelerate. So that means that the frictional force has to be exactly the same, right? Because these forces, let's draw. So for this one, there's me. So I'm pushing, there's a force of me, and then there's a static force, right? So I blew on it 0.01, but the friction was strong enough to withstand that. So these forces have to cancel, so the friction is the same. Right? I mean, look, if the frictional force were greater than my force, what would the thing do? It would accelerate, and it didn't accelerate. So if I exert, 0.01 this way, the frictional force is 0.01 that way. Okay, let's do this one. And I'm going to blow really hard. Okay, so let's say that was 0.1 newtons. Well, did it accelerate? No. So if I exert 0.1 newtons this way, what's the static frictional force? 0.1 newtons that way, because the acceleration is 0. So, all right, now I'm getting ticked off. I'm going to move this thing. Pinky power. Ready? Okay, 1, 2, 3, go. Wow. So I pushed on it with 1 newton, and it still didn't accelerate. So I exerted 1 newton this way. It didn't accelerate. So friction had to be 1 newton that way, right? If it were greater than 1 newton, it would accelerate that way, which would be kind of weird. So the frictional force is 1 newton. Okay, now I'm going to push it 5 newtons. Okay, still doesn't move. So 5 newtons doesn't move. So again, I exerted 5 newtons this way. The frictional force was 5 newtons that way. So the net force along the horizontal direction was 0. So the acceleration was 0, which is what we saw. All right, last chance. Come on. Okay, I'm going to push it, and I'm going to blow on it, just slightly. Whoa! I accelerated it. All right? So this was the max, right? This was the maximum static friction. If I exceeded that, it accelerated, and so it's no longer static friction, it's kinetic friction. Okay? So that's what we're saying. So the maximum is mu n. So what we write, we say that F(s), the max, and you can write that here or here, wherever you want. I don't care. I just put it here. Don't ask me why. So the maximum static friction equals mu Sn. We usually put a little s here if it's static. I'll get to that later. All right? So the maximum static is mu Sn, which for this example was 5 newtons. If we exceed that, it's not static anymore, right? It accelerates. So then it's called kinetic friction. So there you go. All right. So here are 3 models for friction that we'll use the entire semester. First one, static. I just went over that, right? Static friction, Fs less than or equal to mu Sn. Fs max, mu Sn. Mu S is called the coefficient of static friction. You either look it up or you determine it experimentally. Kinetic friction, Fk is equal to mu Kn. So these mu's are different, right? Kinetic friction, Fk equals mu Kn. Rolling friction. Have you ever tried to ride a bicycle with a flat tire? Doesn't work really well, does it? So rolling friction, Fr equals mu Rn. So you can see, that all of these frictional forces, they're all same pattern, right? All of the frictional forces, they're equal, well, they're proportional to n, and then to write it an equal sign, here, yeah. So all of these frictional forces are proportional to n. But to get it to be an equation with the equal sign, this one has a mu s. This one has a mu k, kinetic. This has a mu r, rolling. All right. And oh yeah, one more thing, forgot to show you. All right, have you ever noticed that this box is stationary, right? Once you get it going, it's kind of easy. You know, once it's moving, it's kind of easy to get it going. So try it someday. See what you come up with. So what we learn is that typically, for most things, the kinetic frictional force is less than Fs max, right? Again, what this says is it's hard to get it going, right? But once it's moving, then it seems like the friction actually decreases a little bit. All right. Now, notice these are forces, but I don't have any vector signs on them because these are only the magnitudes, okay? But what's the direction? Well, the direction is always opposite to the direction of motion, right? Friction doesn't help things move. It makes it difficult. So friction always opposes the velocity. Okay. And you know, these are just approximations, right? These are just approximations. They're not laws of physics, you know. All right? I mean, for some objects, they don't even work. But as far as we're concerned in Physics 105, they always work. Okay? They always work. Transparency sheets, you know what a transparency is, old-fashioned, right? They don't follow this at all. Rubber sheets don't follow these equations at all. But that's okay, good enough. Now, yeah. Okay, so here's the question for you. Okay, I want to kind of discuss these coefficients now, coefficients of friction. And again, you look them up or you determine them in a lab. So here's a question. So here's a train. So why are these train wheels made out of steel and not rubber, you know, like cars? Okay? Why do you think? Well, hopefully it's obvious, right? To reduce friction. And here's the proof. So these are coefficients of friction, and here's the materials. So look, rubber on concrete, the kinetic coefficient of friction is 0.8. Steel on steel, 0.6. So there's less friction, right? So if you want to have an efficient train, you want as small as friction as possible if you're going along a level road. So that's why steel on steel. But look at this, it's rolling. I shouldn't forget about this. Who cares about this? It's rolling, sorry. This is what we care about, right? So rubber on concrete, 0.02. Steel on steel, 0.002. So this is a tenth as much as that. So that's what we care about, right? All right. Now, here's a question for you. Let's say you have this big mountain. You have this really, really long train. How is the train able to climb the mountain? How come it doesn't slide down? I mean, think about it. It's all that mass, right? It's all that mass in that train. So gravity is pulling down on that train. How is the train able to make it? Well, here's a situation where you want friction, right? You want to have a lot of friction so the train doesn't slide down. So you're going to laugh when you see this. So this is what they do, and I'm not joking. This is full of sand. And so when they start climbing these mountains, they just open this thing up, and so the sand comes out, and the sand goes on a track and creates more friction. Ha! Isn't that amazing? All right, but that's how it works. So why do racing cyclists pump up their tires each day before a race? Well, to reduce rolling friction. Okay, that's why you do it. All right, so so I'm going to give you two questions. These are incredibly important, and I really mean that. Conceptually, they're very important questions. So pause your video and figure it out. All right, we're back. So let's talk about it. The picture below shows a person exerting a constant horizontal force F on the box. The box moves along the floor with a constant horizontal velocity V. So I would underline this for sure, or circle it or something. The magnitude of the force that the person exerts on the box. Now, you don't have to do this, but it wouldn't hurt. Draw the force diagram, you know? So let's do it. And our concern is with the horizontal forces, so let's just do that, right? Okay, so the person is pushing with a force F. Now what's the other force? Friction, which is opposing, right? So, right? Now, the thing is moving, correct? It says it's moving with a constant horizontal velocity v, so this is kinetic friction. Now, constant velocity. So the sum of the forces along the x direction is 0. What is the sum of the forces? It's big F minus Fk, and that equals 0. So big F equals Fk, right? All right. It's not accelerating, so the net force is 0. So the frictional force has to equal the force that the person exerts on the box. So the magnitude of the force that the person exerts on the box is equal to the frictional force on the box. Right? Makes perfectly good sense. Okay, now the tough one that people mess up on is the next one. Referring to the previous question, if the same person now exerts a horizontal force 1.001 F on the same box across the same floor, what's going to happen? So pause your video and think about it. Okay, we're back. Now, on the previous question, the F was equal to the Fk. But this question, we don't have F anymore. We have 1.001 F. In other words, a larger force. It's not much larger, but it's larger. So now, and remember, same box, same floor, same everything. So now, this is not equal to 0, right? Because this now is bigger than that. So this force is bigger, right? So now we have 1.001 F is bigger than Fk. All right, so this is not true anymore. So now it's a situation we have the sum of the forces equals ma, right? Which is 1.001 F minus Fk. So now it's going to accelerate, right? It's going to accelerate now. All right, so what does it mean to accelerate? Well, look at what does it mean to accelerate? Acceleration means a continuously increasing speed. All right? This is totally wrong, because a constant speed, that means it doesn't accelerate. That means that if it has a constant speed, the forces would be equal. They're not equal. Okay, 3 is crazy as well. 3 says the box would move with an increasing speed for a little while, and then it would go as a constant speed. Well, why is that? I mean, that's kind of crazy, right? If you have an increasing speed, that means that the forces are unequal. You can't all of a sudden start going with a constant speed, because that would mean that the forces would become equal somehow. So you better understand this, so think about it. This is really important. You'll see this question perhaps again. All right. Now we're going to talk about drag. All right, drag. Oops. So, not just air resistance, but things like molasses. Anyway, drag, okay? Drag. Drag is actually incredibly complicated, super complicated. So, what we're going to do, we're going to look at 2 extreme cases. All right, the first case is called inertial drag. Inertial drag. So the drag forces, they're due to inertial forces. So what am I talking about? Like there's air in this room, right? So if I start running this way, you know, the air molecules are exerting inertial forces on me. Or like if this place were filled with water and I'm trying to run through the water, there's inertial forces that are making it difficult for me to run through the water. Okay? I mean, basically, think about it. You know, if there's a lot of air, I have to push my way through the air, right? If there's a lot of water, I have to push my way through the water. So those are like inertial forces. So it's called inertial drag, okay? Pushing those air molecules out of the way, pushing those water molecules out of the way. If you ever run or cycle from like Kahuku back to Laie on a typically normal day, you understand what I'm talking about, because there's usually a lot of wind hitting you in the face. But if you go away from Laie towards Kahuku, then the wind is pushing you, so it's nice and easy. Okay, so this is complicated. Look at that horrible equation. All right, so the drag forces for inertial drag, like air and water, is proportional to rho. Okay, rho is density. Okay, rho is density. V squared is the velocity of the water or the wind relative to the object, to the runner or the swimmer or whatever. And L is something like, has to do with the size of the object. Okay? All right, so I have some real data to show you. Okay, so this is me. I rode my bike to Waialae Beach, which is 7.5 miles from here. And this is from Laie to Waialae Beach, where the wind was pushing me. So you can see that my average speed is up here somewhere. Then I turned around, so now now the wind is against me. So what happened? So here's the average speed here. Whoop! I slowed way down, right? Because it's hard to cycle against the wind. So that was a windy day. Strong winds. Now here's a day I went to Sharks Cove, and there was hardly any wind at all. So here, Laie to Sharks Cove, then I turned back and I came home. What do you notice? Basically the same. So the drag was pretty much insignificant. All right. So that's inertial drag, wind, wind. Okay, there's another kind of drag, which is called viscous drag. And here, the drag forces are due to viscous forces, like the attractive forces of the fluid, okay? If you try to push something through molasses, the object has to somehow free itself from that sticky molasses, okay? So that's viscous drag. And again, another messy equation. So eta, this is an eta, Greek letter eta, that's called the viscosity. So molasses has a high eta, water doesn't. Okay, V is the velocity of the object again, and then L is something like the size of the object. Okay, now sometimes drag results from both of these, the inertial and the viscous. Oh my gosh, what are you going to do then? Okay, so what do you do then? This is called the Reynolds number. If you're a pre-med student, you have to know this, believe it or not. All right, so the Reynolds number, and I don't know, so this is called RE, I suppose, for Reynolds, right? So the Reynolds number is RE. It's the inertial drag divided by the viscous drag. And again, here's the inertial drag, here's the viscous drag. So one of these V's, right, this V, so this V cancels one of these V's, and this L cancels one of these L's, so you just get density, velocity, size of object divided by the viscosity. Okay? Now, so all we're going to do to keep it simple, we're going to just talk about, like, you can have a large Reynolds number or a small Reynolds number. Okay, if you have a really, really large Reynolds number, like 1,000 or something like that, well, what does that mean? If this is a big number, it means that the inertial drag is much, much bigger than the viscous drag, right? Okay, if you have a really small Reynolds number, like less than 1, it means that the viscous drag is more important than the inertial drag, okay? So, and then there's everything in between, right? All right, so I'm not going to write the equations, but you should look at them in the book. So they have equations in the book for high Reynolds number, for low Reynolds number, and so forth and so on. So just look up those equations in the book. Now, here's kind of a real-life example, which I was kind of amazed about. All right, so January 15th, 1919, in Boston, Massachusetts. So that's on the East Coast, and this is January is winter time, so it was cold, right? It was cold outside. And this thing here, it's an elevated storage tank. And it stored, they had molasses inside, all right? They had molasses inside. And unfortunately, the people who built it, they didn't do a very good job. And so the supporting structures collapsed. And so this big giant tank of molasses, it fell to the ground and broke. When it broke, it released 2.3 million United States gallons of molasses. And they came out like a wave. Okay? So just think of this wave of molasses, 2.3 million gallons. And the wave initially was 25 feet high. That's like 7.6 meters high, 160 feet wide, 49 meters wide. And initially it was going at 35 miles an hour. All right? So that was mostly inertial drag initially, right? Just whoom, inertial drag. But then, it's cold outside. And so what happens to molasses when it gets cold? Then the viscosity starts becoming important. So because of the cold temperatures, then the velocity started slowing down because of the viscous drag. And then the viscosity became more important than the inertial drag. By the way, 21 people were killed, 150 people were injured. There you go. 2.3 million of molasses. A wave of molasses. Crazy, right? Okay, let's have some questions here. It's August in Colorado in the United States, which means it's hailstorm season. Okay, a hailstorm is when you get hailstones. A hailstone is a frozen piece of, it's frozen water. It's a hunk of, like a hunk of ice. And they can get the size of baseballs and softballs. Okay, suppose the drag force on a softball-sized falling hailstone continually increases, right? So the drag is getting larger and larger and larger. So this is the inertial drag. So remember, the inertial drag was proportional to rho v squared L squared. All right? So come on, it's falling. So that means, gravity's acting on it. So it's going to go faster and faster and faster, right? And so the density is not going to change, the size is not going to change, but since it's free fall, so velocity increases because of free fall. So if the velocity increases, the drag increases, right? Okay, so the drag force on a softball-sized falling hailstone continually increases until it equals the weight of the hailstone. So draw your force diagram. Huh? So there's your weight, and your drag opposes motion, so it's up here. Okay? So there's weight this way, drag this way. Describe the hailstone's motion from this point on. So pause your video and figure it out. All right, so I kind of gave you the answer, right? All right, it says, so the drag force, we understand why it gets bigger because of that v squared. But then it says it increases until it equals the weight. So this force equals this force. So therefore, what's the net force? 0. If the net force is 0, the acceleration is 0. What's that mean? That means that the velocity is constant. So let's say it was going, I don't know, pick a number. Let's say it was going 10 miles an hour when the drag force became equal to the weight. It would just keep going 10 miles an hour, right? It wouldn't go any faster or slower. It would just keep going 10 miles an hour because the acceleration is 0. So there you go. The hailstone stops accelerating because the net force is 0, and it moves with a constant velocity. Now that constant velocity is called the terminal velocity, okay? So, so you drop, something goes faster, 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 faster. But what we're saying is at one particular moment, the drag equals the weight. So that velocity right then, which stays constant for the rest of the fall, is called the terminal velocity. Okay, so what I want you to do now, so this is the equation for a hailstone, all right, the drag on a hailstone. Look it up in the book if you don't believe me, all right? So that's a drag force. You know what the weight is, so please use your force diagram and figure out an equation for the terminal velocity using this and this. So do the algebra, please. So pause your video and do the algebra. Okay, we're back. Okay, it's this. And again, all you have to do, so all you're doing is you're saying that the drag 1/2 CD rho AV squared equals mg. Then just solve for the velocity and that's it, right? So, sorry, when this is equal, the velocity is called the terminal velocity because it's not going to go any faster than that. So just solve for the velocity and you get that. And I'll leave that to you. And this is a good time to stop.